Hello Internet, welcome back to our Voxel terrain. In this video we are actually going to get our marching cubes working. I hope. So I've never implemented this before, I have no idea how this is going to go. But we're going to try it and see what happens. So the way marching cubes work is, right now we have each of these nodes and they are a tile, they're a tile type. We're going to change that. So instead of being tile types, they're actually going to be the corners. So normally we have like each of these as a tile. We're going to actually shift these entire squares a little bit down and to the left. So this is our first tile, and then this is our second, and this is our third. Well, first, second, third. And it'll use the middle of those as the 4 points, and we'll build a square from there. And then based on those 4 points, it's going to construct one of 16 different combinations of meshes. That's the hard part. So I actually have, somewhere back there, I have a new whiteboard, and I kind of drew up the 16 mesh designs we need. I'll throw up a picture somewhere in the video. So what we're going to do is we're going to write a new quad mesh creator that's going to take the lowest level array, the lowest leaf node array, and then from that we're going to build the entire thing, and that should just work. So I'm not sure how well this is going to go. Like I said, I've never done it before, so we're starting small. This is only 8 by 8, but it should be enough so we can actually test this out. So I'll also put some links into the description of some of the references I've used. So I've read a few things about other people that have implemented these and what they've done. One really cool one about using it to render metaballs. And they actually go a little bit further and do some linear interpolation to get even smoother edges. We're not going to go that far yet. We might get further. But for now, we're going to stick to the basic 16. So we've got this quad mesh creator. We need to create a new one, which we're going to call our marching squares. Did I say marching cubes earlier? I think I might have. We're doing marching squares. Marching cubes is the 3-dimensional version. It's what you normally see in like a 3D voxel terrain. We're not doing that because we don't have 3D voxel terrain. Theoretically, we could expand what we have to actually cover that. We could just replace our quad tree with a octree, and we'd pretty much be good. We just have to change how our meshes were generated. Just do it in 3D. And the algorithms aren't too difficult. If you've done this, you can expand it into 3D. I don't think we'll actually get into that because I don't know if there's a reason to. So if it is something you guys want, well, we can certainly look into it, but I don't see that being a thing immediately. So all I did was copy things from our quad mesh to our marching squares mesh. It should do the exact same. So I'm going to actually stop this and replace our quad trees version with our new version. So one of the things that's going to happen when we do this is we are actually going to lose a little bit of our stuff. And the reason for that is because we need to use each of these as points. So that outer edge, we're losing half of our minimum size. Did I call it the terrain material? I think so. So this should get us the same mesh. We have to generate it. There we go. It all works, does the same thing. So it's doing the exact same thing. There's no difference here. And that was sort of the idea. So what I want to do is I want to pull out this generate mesh and actually abstract it away, and then make 16 unique shapes that we can generate and insert this way, which is going to be gross. So how do we want to do that? We're gonna stick with the quads for now, just because there's some refactoring I want to do beforehand, just to get this to the point. I probably could have done this off camera, but this will work. So what I'm going to do is I'm going to abstract this out. Just extract into a method. Resharper should grab all of the variables. And then we will just do insert. We want to insert a mesh. Yeah, because we're going to be, there's 16 unique combinations. One of them is blank, so that's easy enough. The other, and one of them is full. But anyway, we'll get to what the shapes are when we get there. But for now, all this should do is accept a ton of lists, and then we are going to actually build our thing. So eventually we're going to want to replace this quadtree node with our list, and then the index. How are we going to want to do that? With the index of what we want? Yeah, I think that'll work. Well, we may have to tweak that a bit. Maybe pass in the 4 points and then figure it out from there. Yeah, I think that makes the most sense. So anyway, I just extracted a method. It should still compile and work. If it doesn't, then things are broken, but it's fine. Cool. So everything is still working. We're still doing all of that. So no, we're going to keep it. Do we want to? So I'm going to pass in 4 points here, which are going to be the 4 quadtree nodes that we're going to do, or to mess with. So these points are going to map to, where was it? In here? Yeah. So the indices of these are going to map to this quadtree index. And that's just so we keep consistent throughout it. So that'll be the 4 points. And we can actually use those to index into this array. But for now, we'll just make a new array. Something like this. Does this work? Maybe. Sure. What am I doing? I don't think that works. No, that doesn't make any sense. We gotta pull that out. There. Cool. Done. So now we have, all we replaced this with was we're passing in a new array. Now that I think about it, let's not do that. let's just start with this. It'll just be easier. Yeah, because all I'm gonna do is go down some rabbit hole that we don't need to go down. So we'll do left top, or top left, top right, bottom left, and bottom right. And those will be the 4 points we're passing in. And those should map to this. Top left, top right, bottom left, bottom right. Good, they do. So we'll need 4 variables for that. And for now, I'm just going to set them equal to the leaf. So these are going to be the 4 nodes that we're going to need to find. And then we're going to pass them into that function. That function is going to figure out what mesh to create. And then it's going to actually add the values onto each of these lists. So I don't know, again, if this is the best way to do this. I've never done it before. So we're going to do exactly what we do in every video. I'm going to make things up and try to get it to work. And then in the future, once we actually figure out what we like and what we don't like, we can go back and pull things out. Or you can take it a different direction. That's kind of the advantage of programming. There's no right solution. There's just a bunch of solutions. And depending on what you need to solve, you choose the best solution for you. So we pass in the exact same leaf for each of these, which admittedly not the best way to do that. But we're going to do points 0, And I'm just going to slowly stick this in here, which, again, probably not a good idea, because we're going to be abstracting it out again. But I'm kind of trying to take small steps, because if I try to go like in a really long thing, it probably isn't going to end well. So everything still works, which is good. We haven't broken anything yet. So our next step is the fun one. We get to iterate over our array, which we're going to want not this. We want where the nodes.data is not 0. We actually don't want to do this anymore because we can't. Because even if the data is 0, that's only one of the points. So we need to look at 4 points before we figure out what to do. So our insert mesh is going to handle all of that logic. It's going to take these 4 points, look at the data in the 4 of them, figure out which mesh to do, and then each of those is going to have something that looks like this to do it. Which, thinking about that may result in a lot of extra code. So we can probably figure out a way to make that better. But for now, we're going to make it gross and we're going to make it work. And we'll figure out what we don't like later. So for now, I'm going to do an x-axis, where x is less than the size. So this is going to be a little bit tricky, because so if I just generate this, is going to break. Didn't break. Did I not save? Anyway, so like I said, we need the 4 points. So actually, if we take the full size of this, if we take 8, this is actually equal to 2 to the power of the depth to get this width. If we do the full length, we'll take 2, 2, 2, 2 across, and then we'll get to this node and try to take the one to the right, and we'll get an out of bounds exception. Actually, since it's a linear array, we'd actually get this node, which is still wrong. So we have to actually do 2 to the 8th power minus 1 in order to get that, so that'll actually be our size. So let's calculate that. Our size is going to be a integer of the math.pow of 2, and the reason we're using 2 here is because it's a quadtree and we're only doing 1 dimension. So a quadtree has 4 elements, obviously, but only 2 across the horizontal or vertical axes. So now we need our quadtree depth, and we need to subtract 1 from that. And then we just need to remember that this will go to the final node. We just need to add 1 to each of those to get the next adjacent node. So then we add x, and we'll do the same for our y. Let's actually initialize this correctly. And we should be good after this. So we're not totally good, but we're getting there. So this is going to iterate over our array. What we need to do now is a little tricky because we actually are going to need the full size as well. Because our y, the actual index that we're starting at, so we're going to have a top and we're going to have a bottom. This is weird because we have a linear array, not a 2-dimensional array, so we have to actually index into the 2-dimensional array. And to do that, we need a top row and a bottom row because they're not going to be adjacent to one another. So we're going to have our top equal to our x plus our y times our size plus 1. So this will be 8 again. There's no reason for us to recalculate that, but we definitely need 8 here so that it skips over that many rows. So going back here, yeah, we lost it because it compiled. Anyway, we're going to iterate over, if we're on the first row, which is weird to think about because 0, 1, if we're on the 1 index for y, that is actually 8 plus our x to get to wherever we are, because 8 is the entire sum of the first row, and then we need however many additional, which is our plus x here. So this should get us the top row, and then we actually are going to need plus 2. Is that correct? I don't know. So we should get it back now. I may need to restart, but we should get our tree back. So if y is equal to 1, we want to start here, which will be 8 plus x, which would be plus 1 here, which would get us to that point. And then our next one is going to be plus 2. So if this is equal to 7, is that correct still? I'm not sure. Because it'd be equal to 7, which would get incremented to 8, which 8 times 8 is 64. We might get out of bounds errors with that. Let me put a conditional breakpoint on here. I'm pretty sure, just thinking about this, our bottom is going to be greater than 64. And our top might get close as well. So we're going to stick a conditional breakpoint on here. I think that may need to be a bit higher because I don't know if that will actually work. So we're actually not going to do that because it wouldn't have been set at that point. It wouldn't be defined. So we're going to debug log our bottom. And then we're also going to throw out our x value plus our y value. So this is gross, and we'll definitely take this out. But there we go, fixing some references. But anyway, it's gross, but it gets us what we need, which is sort of the rule of the game at this point. So we get here. It doesn't appear to be going out of index, which is good. I think that's correct. Why would that be though? I would expect this to go to out of index. So we get 8 and then plus 1, which is that's just confusing the way I'm doing that. I don't really like that. But 8 plus 1, this only goes up to 7, which might be the reason. Yeah, I think that's the case. Okay, never mind. I'm convinced that may actually work. So we have our top and our bottom. We need to pull those in, which we can do like this. And then all we need to do is actually index. I deleted that too fast. But we just need to index into those positions. So we are going to take our leaves and convert them into an array. This is not how we should do this. We send out an enumerable list. I'm going to call toArray on that, which is going to be slow. We'll want to change our quadtree implementation so it actually just returns that subarray. but I'm not going to deal with that right now. It's fine if this is a little bit slow because I'm not super concerned about it. But you definitely shouldn't do this for production. So we get our leaf nodes and we just call toArray. Okay, that's bad, but anyway, it works. So we can do our leaves and then do our top index, and then our bottom left is also going to be our leaves.bottom, and then our bottom right and our top right are just bottom plus one. Whoa. Plus one and top plus one. So we'll take the two indices and then we'll go one to the right in both of those and select both of those. Then we pass it into our insert mesh and we get that information. Now I'm going to modify this one last time before we do anything crazy. We're adding all of this voxel information. I'm going to do our quadtree index, is that what we called it? Top left. Really? Don't make me actually... Fine. Okay. It's not going to be nice. So I'm actually going to pull this in like this. And we're going to do that for all of this other information. So our UVs should be fine? Question mark. But for everything else, we can actually replace these with actually less math, because we can just do points 0.position and just take the center position for it. And we can just take the center point for each of those, and it should actually center it for us. Assuming I'm thinking about this correctly. Which I hope I am, because if I'm not, then this is not going to work. But there may be some other issues with this, but we should see the first major change with this change. We should see... What the heck? We definitely saw a change. That's definitely not wrong. Well, okay, it's definitely wrong. What the heck? What have I done? Before we cancel, I'm going to actually turn on the wireframe just so I can see where things are going. It looks like we're wrapping incorrectly. I'm going to remove everything and slowly start inserting. Oh, I bet I know what's going on. Or part of what's going on. It's still broken, but not totally broken. I don't think. I hope not. No, it's totally broken. What am I doing? Upper left. Cool, initial index. Oh, okay. Right, that's just for doing that. I have done something horrible, and I think it has to do with this. But I'm not sure what. So I'm going to revert this bottom change. And do y plus 1. Just so we increment our y. That shouldn't change our calculation at all. But that's more just as a sanity check. Just to make sure I'm not going insane, which is possible. So we're still getting the wrapping. We're getting some weird... So part of this weirdness that's going on is due to... No, it can't be due to that. I'm not sure. It's being weird. Obviously, it's wrapping incorrectly. And we're off by more than one. It looks like we're incrementing too much or something because this isn't right. We're getting every other index is screwed up. Because like here it goes that way. Let me turn this off and actually enable shading. Yeah. Okay, so some of our stuff is going on the back side, which means we screwed something up. Well, I screwed something up. I think it has to do with our vertices order. Top left, down. That seems correct. I don't know where to go with this. It's stuck. Well, I'm stuck. Something here doesn't make sense to me, but I don't know what it is. So I'm actually going to go here. Let's swap out this data and just plug in 1. And then what we're going to do is if our points dot, or if there's just any point p where p dot data is equal to 0, then we'll just return. So if the initial point is 0, we don't draw it. This way we should only get, well, it'll still be weird. Yeah, super weird. Okay, still broken, but we can actually delete stuff now. And so what this is doing is it's not drawing anything with a point that is null. Which I can't fill in like that square, but if I go over here, I fill in all of those. So our indices have to be screwed up. They can't be right. I bet that's our problem. We have a heap. This isn't how you get that out of a heap. That won't work. That would be nice if it worked, but it won't. Because things are subdivided, which is why this isn't working. I should have realized that sooner. But we're using a heap to store this, which means we have to do more. Do we want to use a heap? We could just use a flat array at this point. That would actually be way easier, like significantly easier. And the advantages we'll gain from this, I have plans to take that out. We'll persist with this just because it seems useful. But we need to figure out a way to iterate over our heap and make it less bad. Okay. I've got an idea. Oh, this is a really bad idea. So we effectively need to sort our quad tree, which we can do. We can order by our nodes, node.position.x, and then by, oops, that's not right, then by the nodes node position.y. This will work. Something it doesn't like that, but it will work, maybe. type arguments for method cannot be inferred from the usage. Okay, what? Oh, is it really returning our vector? Why would it? Node position dot why? Oh, duh. Sorry, going insane. It's fine. This is fine. I'm not. Okay. Problem was capital Y. Case matters. So we have now ordered it by our x-axis and then by our y. I think we may need to flip those. But we should be able to work now. Yeah. Huzzah. Okay, so all we've done now is make our quad tree less useful. But we're kind of almost there. It's 30 minutes in and we're finally actually able to start marching cubes. Probably could split this up into episodes, but screw it. We're here. I'm here. It's midnight. I have work in the morning. Let's do this. So what we need to do is actually be smart about what kind of mesh we need to generate, which is what all of this is actually going to cover. So now we have 16 cases we need to cover for this, which is going to be fun. Don't know how we're going to do that yet. Yeah, that'll work. So what we're going to do, will that work? Yeah, it'll be fine. Okay. We're going to make a flag. Is that really? No. Not really what I want. We're going to make a set of flags. So we have a public enum marching squares patterns. So there's 16 of these. We're going to use a bit mask. I don't know if that's a good idea or not, but we're going to do it because why not? So empty, that's easy. That's 0. Full. We're going to want to order these, but for now, I'm just going to input them like this. We'll go back and convert those into binary, or something we can actually use. So this would actually be 15, 1 plus 2 plus 4 plus 8. But anyway, we can get to that, and we can't use those. I'm just going to use binary because it explicitly says what it is. So each of these are going to be our top left, top right, our bottom right, or bottom left, and then our bottom right. That's what those are representing. And we only care if there's something there or not there. We don't care if it's 1 or 2. Our shader is going to handle smoothing between those. So we only care about this, which is going to be fun. So top left corner is going to be 1, 0, 0, 0. Top right corner is going to be 0, 1, 0, 0. And we just got to go through this. So I'll write these, and then we'll pick back up once that's done, because this is just busy work. Okay, we've got them all. This is what this is going to look like. So I need to convert these into binary, and then we're good to go. So quickly just walking over what these are. We've got, each of these is representing one possible configuration. It goes over all possible configurations. So if there's just one actual input, you've got the corners. That's what these are. If there's 2 adjacent, you end up getting sides. If there's 2 that aren't adjacent, there's only 2 possibilities for that, and they're both diagonals across. That's actually a special case in marching squares and in marching cubes too, because you don't actually know what the priority is. So it's kind of up to your implementation to figure that out, because you either have a line one way or a line the other way, or you have things meet in the middle, which doesn't really make any sense. So we'll have to figure that out when we get there, how we want to implement that. And then the next four are the top are just empty corners. So it's the exact opposite of a normal corner. It's where 3 sides are filled and 1 is missing. And then the last one is just full. So if it's totally full, then it's just all sides are there. So what I'm going to do is I'm going to go through this, and then I'm going to replace each of these with their actual value, and then we'll move on and actually implement each of these cases, which might take a bit. But it's mostly busy work, so I should be able to cut most of that out, and then we should be able to get it working today. That's the goal. Whether it works or not, I don't know. Haven't done it, but we're going to try. So I'll be right back. I need to get this all working. All right, so I've got them all converted. They appear out of order now just because binary is weird. Well, numbers aren't supposed to be designed like flags like this. But that should be fine. It makes sense, at least to me. They're all ordered by the number of positive edges. Regardless, all we need to do is actually calculate. We can pull this out because that's no longer needed. We need to actually calculate, based on these 4 points, what the value is. So all we should do is pretty much do a bunch of shifts and then calculate our resulting flag value. So to do that, all we need is a starting thing. So we'll do a type. I don't like using type as a name because I think it's a keyword. At least in a lot of languages, it turns out to be a keyword. It's like class. You just don't call things classes, just because then you have to come up with all sorts of funny names to name things, and it's not great. So we've got our type. So with our type, what we need to do is just do 4 bit shifts and ands. So I'm going to do an or equals for each of these, and we're just going to do points 0. Actually, we can do this better. Let's do a for loop of I, and I is less than the points length, and just increment over each of them. And then what we want to do is do type, well, if our points I dot data is not equal to 0, then what we can do is we can increment it. So type or equals. So we're going to use an or here, and then we're going to use a bit shift. So we're going to do 1 bit shifted left by I points. So we're taking our flag and moving it across. So for our first index, it'll be that. For each of them, it will change. This isn't actually going to work, though, now that I've actually written the thing, because the way we structured our data up there, our top left is the 4th bit. This would make it the first, going from right to left, which isn't necessarily correct. But anyway, so we're not going to do that. It seemed like a good idea, but no. So instead, we're going to use a ternary operator because it's one of the few times when it actually makes some sense. So if points.data is equal or not 0, so if there's something there, then we want to do 1 bit shift 4, bit shift 3. Otherwise, 0. I really don't, we're going to have 4 of these. Is this really what we want? Bottom left, bottom right. No, I don't think I like this. This is going to confuse everybody. Okay, one sec. We can do this better again. The embedding round 2, I guess. Undo. Why are you so slow? There we go. So what we can actually do is do 4 minus I, 3 minus I. Because we'll have 0. Because what I actually did is I inverted it. I went from left to right. I could actually go up here and just invert each of these numbers and it would work. But we can just do it here instead and it will do the same thing. So this is going to calculate our type. We should actually get a value out of this. And then we just get the wonderful switch on our type with 16 possible mesh generations. This is going to be the fun part. So the good news is we do have one that we can ignore. So we have our marching squares patterns dot empty. We actually need to make a case statement there. But when we get this, we can just break. Because this, it's just empty. There's nothing, we don't need to put anything there. It's just empty space. Can't convert to int, but we can convert this to a marching, ooh, that's not right. Marching squares patterns. Yes? No? Maybe so? We definitely need one of those. There we go. Done. So I'm going to quickly pull each of those down into this case statement, and then we can do this. We probably, once we get this implemented, there's probably ways to optimize how to do this, because a lot of these are going to be similar patterns, especially like the sides. We can probably combine those and make those better. I'm going to do it the greedy way, the simple way. And then we can isolate those patterns and pull them out later. It's probably not the best way to do this, but this way we'll see the wrong way to do it. I don't even know if it's wrong. Don't know if there's a better way to do it, but this way we'll kind of go slowly instead of just hammering at things until it works. So another cut. I'll be right back. Going to just pull things in. Okay, so here's our switch statement. It is awful. I don't recommend writing switch statements this long. I mean, they're better than if statements, but this tends to not be maintained well. The only reason this is probably fine is because this isn't going to grow. But usually, at least when I've seen it in production, when you have a switch statement like this, somebody comes in years later and adds 2 more cases, and then people keep adding more cases and more cases and more cases, and eventually you end up with like 1,000 lines, which nobody likes. At least I hope nobody likes. So normally switch statements are nice because they're constant time if statements. So if I wrote this as an if, it would have to do each check individually. With this, we immediately get to where we want, which makes it faster than an if, but that's still gross. And you have to do like the fun control structure stuff. So it's not, I don't know. I have mixed feelings about switches, but we're gonna ignore that. I was thinking about it while I was writing that. I think we can actually improve this a little bit. So, given our array of points, I think we can write something that will return, or that will at least calculate our thing. How is this going to work? Is it going to work? No, never mind. Ignore me. That doesn't make any sense. So, do I want to do that? No, I really don't. Okay, this is going to get really bad, and then I'll probably end the video, and then I'll come back and fix it all and show you guys what I came up with. Usually refactoring takes a lot longer than writing code, which is why it's just harder. So I don't know. We're gonna, yeah, this is gonna be fun. Build full square. Yeah, build square full. Yeah, I really don't like this. So we're gonna have 16 functions to generate each of these. I know that sounds like an awful idea, and it is. You're correct. But the advantage to that is it's relatively straightforward, and it's linear. So we can, when we write it like this, the similarities between all the functions are going to be blatantly obvious. And so my goal is that we'll be able to take that and actually figure out how to fix this so it doesn't suck. So that's sort of what I'm going for, is just make it bad so that you can see what's good about it and then kind of pull that out. So we're going to write a lot of these. I'm going to actually quickly skeleton. I'm going to write some skeleton code, so there'll be another cut here. But I'm going to write some skeleton code for each, because we have 4 more distinct types. We have our big corners, then we have our sides, we have our diagonals, and we have our corners. Each of those are going to be unique. Our full square actually is already working. This is our full square. That's done. So we just need those other 4-ish types. I forget. Yeah, 4 types. So I'm going to write all of the functions for them, get them all laid out. And then we'll have like one that we can write and then translate that to the other 4, because the logic's going to be the same. I hope. If it's different, then we've got other problems. But hopefully this will make it go a little bit faster. So I'll be right back. I'm going to do that. Okay, so to illustrate the issues you have with switches, this is our switch statement now. That's only 16 switches and 2 lines in each. And it barely fits on my page. I had to close the console to make it fit. This is gross. Don't do this. Even if you think it's a good idea, don't do this. Remember this? Temporary. We're getting rid of this. I want to make that very clear, because you don't want this in your final code, because somebody's going to come and screw that up and you're never going to find it. So just throwing that out there. What I did is I created a new function. Some of them are blank. And so I created one function for each type that is a copy of our full square. And then the other ones are just empty. And that's just because we're going to copy and paste the results. So I think we can get started. We now have 500 lines of code almost. That's great. It's going to get longer. So I imagine by the end of this, we are going to have probably close to 2,000 lines of code. We're not going to write 2,000 lines of code, but we're going to have it just because whatever. So in the old days, we'd be doing great because we wrote a lot of code. In the new days, we're doing awfully because we wrote a lot of code. But just to make sure everything is working as intended. Oh God, what have I done? So this doesn't look right, and we're getting all this weird behavior. That's because some of them are implemented and some of them aren't. So they're like turning on and turning back off, and it's broken. Let's just put it at that. This is not what we want, but we can get to what we want. So we're gonna leave this guy for the last. So this is going to be a little bit more difficult because it's the empty square in each corner. So 3 points have data in them and 1 is missing. We're going to leave that one for last just because that's going to require 3 triangles, which is going to just be more work. So we'll skip that for now. We'll do the sides because those are frankly easiest. So if it's the left side, all we need to do, how does this work? If it's the left side, then the left has data, right? I believe that's how we defined it. I should make sure, but yeah, that makes sense. So this isn't correct. Instead, what we want our 2 left positions, which is going to be 0.2 and 0.0. And then we want to go halfway to the right. So we don't want to get all the way to the next point. We want to do halfway, right down the middle of it. So we should actually be going right down the line of our quad tree because that's in between the 2 nodes, which we can do. Is that a good idea? That seems like a really bad idea. It's, like I said, it's easy. So if you lerp between the 2, again, not the best solution. There's better ways to do this, but this one will work. You can just take the 2 positions, like so, and go halfway between them, so 0.5. And that's pretty much all you need to do. And that will take a position halfway between the 2 points. So if we take our 2 top points, get the position between them, that will get us halfway in between. So the reason I'm doing it like this, instead of actually solving this the better way, in a way that actually doesn't require all of that math in order to get just a center, we could do it better, but by doing it like this, we're going to be doing a lot of lerping to get all of our stuff. We're going to need that center point a lot. By doing it this way and doing it consistently this way, we'll be able to find those similar points and then eventually condense all of those down, I think. So I'm trying to keep things as basic as they can be, which is why we're getting this massive code explosion. But hopefully in the end, the result of that is that we can go back and clean things up a bit. Still haven't figured out if I'm going to record cleaning it up or just do it on my own time. I think it might be best to just do it because I don't know what value there is in just watching me go through and be like, oh, that doesn't look right. Let's fix that. Speaking of, let's fix that. So that's pretty much everything we need, I think. All of this, our UVs are going to be screwed up. I'm going to throw that out there right now. Those we're not going to keep up to date. I'm not going to worry about those yet. The idea is our UVs should map directly to these positions. So the solution is to just not write these immediately to the vertices array. It's to actually store them and then write them to both. Not doing that yet. We can do that kind of on our own time. There's no real reason, and the way we were doing it was actually probably not optimal anyway. But I'm going to pretend like this works, which probably doesn't. But anyway, we are going to copy that to each of those, So we have all of our squares, though they should all work. We've got our top now, which means we want these 2 points, like so. So our first 2 points are our top, and then we want to lerp between the top and the bottom. So instead of between 2 and 3, we want to go between 1 and 3, which will be the top or the right side. And then we want between 0 and 2 for the other one. So again, relatively basic. I might cut this out or part of this out, just because it's the same logic. We're just doing it differently each time. It's slightly just moving those around so we get the correct values. And I don't think we're not gonna worry about the UVs again. So yeah, bottom side, same thing in reverse. And remember, it does matter the order you put things in, because otherwise the rotation, the vertice rotation in our triangles will get out of order, which could cause them to flip around inside of our rendering, which we don't want. So otherwise, we could really just copy this and just do it backwards, which we're doing, but just a little bit differently. I think we have our sides done. So we should be able to come in here and test this out. It'll be a little bit hard to tell what's actually going on just because it's not all done. But we do have some sides going on here. So down along here, that's one of our sides. There's another one, there's another one. We doesn't look like we have any on the right side that I can see. There we go. So all of the sides appear to work. So we're getting a side there. Everything seems fine. It's all still a little bit funky just because we haven't completely finished it. And it's all just a little bit not quite right. But we're making progress, and that's what counts. So I guess on to the next one. So the next one is top right. What? Did I do the wrong ones? No. Okay. Okay, the next ones are going to be our top left corners, or our top corners, which is just going to be an actual triangle. There's not actually going to be a full quad there. So these are actually going to be even less than our normal. So for our top left, that's going to be composed of our top left, top right. No, that's wrong. So this is actually only the top left is true, which means we want to go between our points 0 and then 2 lerps. So 2 middle points between our points 0 position and our top left, or top right, sorry. And then our second one is going to be our bottom left, but we're going to be halfway between that and our first position. So in the 2 centers there. So we should do something like this. And so take the position of our first index and then take the index of the next point, get the halfway point. We don't need a 4th index because we just don't. UVs are still going to be all kinds of messed up. They may actually work, oddly, just because of the way that's working, but I wouldn't trust them. But that's fine. What else do we need? We don't need any more normals. And we can just do 1 triangle and 1 color. One thing I do want to change is going to be our voxel color. We'll have to figure out how these colors are going to work. That's going to need some work. We'll probably do that in another video when we start actually really bringing out our shader, because if we do it now, it would actually like fade between them. But depending on how we do that, it may not look correct. So I just want to focus on one thing, get that working, and then we'll expand. So I think this is done. We create a triangle in the top left corner and build it, and that should be it. So let's bring that to the other three, like so. Ooh. And then same as before, just modify them to work for the other one. So this is our bottom right corner, which means we still need our clockwise rotation. So we are going to want our top. We're going to want our top right, which is going to be 0.1. And then we're going to want our bottom point, so 0.3. And 0.5 to just get between half of them. The next point in the clockwise rotation is going to be 0.3, just plain old 0.3, like so. Need to make that a lerp. There we go. And then the final point is going to be between our bottom and our third position. And that's the change we need to make. So assuming everything else is correct, this should get us our bottom right corner. So I'm going to do that for the next two, and then we'll pick up and hopefully it will work. We should see some triangle slices, and with our everything else, it should all start coming together. So be right back. Okay, I think we're good. So we have our four triangle implementations. They're all more or less the same. They look boring, but we should be able to actually see triangles start to pop up. It might be a little bit funky because like here we aren't getting our slope, because this is probably a something or other. That was a bad description. It's probably the missing one piece or something. But anyway, we're getting there. It's looking more and more like what we were trying to build. So the next piece is either going to be our diagonals or the other corner piece. It doesn't really matter which one we do. I think diagonals makes more sense. So let's start there. And does it make more sense? Not really. But sure. Which one do we want? Diagonal or our empty corners? Let's do diagonal because there's only two of those. So we can just get those done. So the way I name these, diagonal left to right means top left to bottom right, and right to left will be top right to bottom left. So this is going from the top left corner down to our bottom position. Actually, this is going to take even more. We're going to need at least 6 vertices for this and 3 triangles. Because, yeah, because we're going to need one at both points. We're going to need one at the middle on each side. And we're going to draw sort of a like crystal shape. So it'll look sort of like a weird diamond with a square. Anyway, bad description. I've got pictures. Those will be somewhere in here. It'll make more sense with the pictures. So we started here, so let's do it. We need to do them both anyway. So it doesn't make sense to hold off. So we're going to do more lerps because why not? Like as you can see though, we're using this lerp function a lot, which kind of indicates to us that we may be able to find some way to get that because we're finding this middle point all over the place. So what I'm thinking is we can probably abstract this down to a single function or like 3 functions for each thing. and that should be a lot better. But whether or not that actually works, we'll have to wait and see. So I lerped and got the middle point in the top. Now we're going to get the middle right side. So that's going to be vector2 lerp of our points. We want our right side. So position 1 and position 3. And then we need our bottom right, which we already have. And then we need 2 more intermediary parts, and that'll make up our 6. So now we're on the bottom. So we want our bottom point, which is going to be 2 or 3 and 2. And then we want our middle left point, which is going to be between 0 and 1. It doesn't matter what the order between those is. It's going to be the same thing either way. Then we also need our UVs. I'm kind of ignoring those, but they need to match up, otherwise they'll all get screwed up. So I'm just going to add those. We need to update our normals as well. And then the fun part, we need an additional triangle. And some additional vertex colors. Lots of stuff. So our first triangle can actually do exactly what it already is doing. Go between here to there. So it'll do sort of a triangle along from the point to there and then down sort of there. No, this isn't going to make sense to explain. How many are we going to need? I think we're going to need 4 actually. Because if I do this, then the next point can go from position 2 or vertex 2 to vertex 3, which will be our bottom corner, and then back to our original vertex. And that completes one side of our trapezoid. It makes a trapezoid effectively. And then we need to flip that over the diagonal axis and do the same thing, but for the other side. And so what that's going to look like is a good question. It's going to look like 3 plus 4. So we'll get our middle point on the bottom, and then plus 5, and that will get our next point, and that will come back, same as we did here. Now we're just starting with our other side. And then with this, we should be able to start at 5 and then wrap around to 0. And then plus 3. So get all the way back to our normal point and then head back to our origin, which is exactly what we did here. So that should complete our diamond shape. It's gross. This whole code is gross. And I'm kind of regretting that. I really don't like this implementation, but I think it's a good way to illustrate the duplicate code in this. And that way we can actually clean it up. Gonna say that a lot because I struggle with this. So for the next one, we just need to do the same thing, but we need to start from top right to bottom left. I feel like my camera's reversed. It is reversed. Yeah, there. So anyway, we need to do that. So I'm going to implement that, and then we can check, see if it works. And then we have one more after that, and it should all be implemented. It should all work. I hope. If it doesn't, we're in trouble. But I will be right back. This should work. Should do that. Hopefully we get done before my camera dies. It'll be great. So, BRB. Okay, I did that really fast, but I think it should work. I hope it works. I don't know how we will know, because it's really hard with it not being fully implemented yet to tell what's going on. So we may have to wait on this for confirmation to see if it's working. But maybe it works. That's not a good argument, but we'll go with it. So final thing is up here, and if we have any issues, then this may extend a bit, but that's, yeah. So top left is empty. All we have to do then is replace this vertex with our empty points. So more lerps between our point 0. To make this easy, I'm actually going to go down first. So do our second point. And the reason we're doing that is because this way, if we keep iterating over things, we maintain that clockwise rotation, which will prevent any of our vertices from being out of order. So all of our vertices are already arranged clockwise, which should make it easier. Going to add the other UV. Don't really care about that right now. And then we just need to come up with how our triangles are going to look. I'm going to copy the color quick. So, what do we want to do? I think we take the opposite side. So in this case, it would be the bottom right, and then we project 3 triangles that way. I think that makes the most sense. So each triangle is going to share that vertices. So in this case, that's going to be +4. Yeah, +4. And then we'll just go from the bottom and we'll do like a fan, because this is the top. So that would be 3. And then the next step is actually just going to be 0. So all of these numbers, I know it's probably hard to follow, but it's just, we're talking about these vertices and getting all of this working, which I don't know how to make it more clear. I could put together an animation, but that would mean editing would take days, which I'm not sure is a good use of my time. But if this is confusing and you guys want more about mesh generation, I do have another series about that goes a little bit more into depth about it. So check that out, or read a graphic book. Those are actually interesting because there's more to do than what I'm doing. Anyway, got distracted again. We have to keep our clockwise rotation as well, so I'm going to keep going around the outside. So we're going to share our 0 vertice, this one, and then we're going to add this new one. So all we're doing is we're actually sharing 2 vertices, and we're just swapping out this like middle one, and we're kind of rotating those through. So this 4 is going to stay, and then we just rotate up. So the 0 moves up space, and then we rotate in a new one. And then we just rotate around our mesh is the idea here. And we can do that because they're all already in their clockwise orientation by indice. So, well, they're not, but ignore what I'm saying. Right, what was I saying? Important. We have to, that's good. Next one. Keep getting distracted. 1 will be our next vertex, and then 2 should be the final one, and that will be our top right. Yeah, 2. There we go. Cool. And that should do our top left empty. We should be able to build a triangle where that part is just not filled in. And I really hope this works, because debugging this may not be very easy or fun, because there's so much duplicated code. I'm going to copy this again, port this across, and then we should be good to go. It should all just sort of work. If it doesn't, oops. So I'll be right back again, hopefully with it working this time. And then if this actually does work, we're done. And we've got full marching cubes, squares, marching squares implemented. It's gross, but it works. And then we can make sure that it scales to higher resolutions. All right, so I got everything sorted. I had to make one change. Oh, I didn't have to, I just did. Just to make it a little bit easier, I moved things around. So we were talking about how everything had to be clockwise. I actually ordered our vertices in all of them, so they are clockwise. And then I redid our triangles, so it takes the last index, and then it just iterates over each of them. So 0, 1, 1, 2, 2, 3, and takes those to make triangles, which is much better, I think. So, assuming everything works, we should, hopefully, get marching squares, which should mean we should have squares around the outside. Hey, huzzah! It works. That's awesome. Okay, so this is marching squares. That seems wrong. I don't know what's going on there. Why, like, the bottom is a line? That doesn't seem correct. But everything else seems to work. So we should be able to test our diagonal. Ooh. Our diagonals are broken as well. But my camera is out of battery. So I will have to do some of this debugging in the next video. It's just the way it is. But for the most part, it's working. There do seem to be a few growing pains, but I imagine we can sort those out. Like, I don't know what that is. No idea. But other than that, it's doing more or less exactly what I wanted, which is good. We get these smooth edges. So next, we can start simplifying this, make it better, go through and actually improve all of our algorithms. And then I've got some really cool plans for how we can actually blow this thing up. We already have like circle destruction. That's cool. But I want to actually use a mask from an image and destroy this. And I think we can do that even better with compute shaders. Okay. As I was saying right before I was so rudely interrupted by my camera running out of batteries. It's still out of batteries, but I think I can get like a minute left. So we're going to use compute shaders to do destruction. I think that's going to be really cool. I don't know how to do it, but I think we're gonna try. So that's to do. Anyway, I'm gonna end quick because camera. So if there's anything you guys want to say, anything you want to see, let me know. I'd love to hear it. If there's any changes you have or refactoring suggestions or anything like that, shoot those up my way as well. I'd love to discuss them or hopefully implement some of them. So yeah, I'm always looking for new project ideas as well. So tell me about those. If you've got some random idea of something you think we should make, I'm always open. So until next time, see you, Internet. Camera's not dead. Yes!